Okay. So I give an introduction of myself, right?
Yes,
Okay.
yes, please go ahead.
Okay, great. Yeah. Thanks so much for the invitation. So I'm Lily Weng. I'm a new assistant professor in UC San Diego, Jalisco Data Science Institute, and I'm affiliated with the CSE department. So originally I'm from Taiwan. I did my undergrad in National Taiwan University in electrical engineering, and then also my master also in communication engineering. So I was doing this microwave circuit in my master's, and then so when I went to MIT for my PhD study, in my first 3 years, I was working on the photonic circuits. So I'm trying to quantify the uncertainties of the process variations for manufacturing the photonic circuits. But I kind of shifted my research focus because I'm always very interested in this in mathematics since my senior high school. So like machine learning really attracts me a lot. So that's why I decided to started my research in machine learning, and I've been working on the robustness kind of the point of view for the machine learning models. I have experience on robust regression to detecting outliers, and then later I moved to quantifying the robustness of neural networks, and that is the topic for today. So I'm very excited to share with you some of the research results and also what is some ongoing research work in my group at UC San Diego. Okay, that's great. So I think I'll try to go over the presentation, and I will try to stop like at certain points to ask if there are any questions or if you have any feedback, comments, and then we can kind of discuss there and then move to the next section. Okay. So we all know that deep neural networks are everywhere in our daily life right now, right? So in a certain traditional artificial intelligence area like computer vision, the most basic task is image classification, object detection, scene parsing, segmentation, and it's also being widely used in autonomous driving, for example, to detect the pedestrian or recognize the traffic sign. We know that it's also being widely applied in natural language processing and speech. So for example, in machine translation, text classification, and speech recognition, just to name a few tasks that have been using deep neural networks a lot. So in fact, deep neural networks are actually more popular than this traditional artificial intelligence area. So for example, in medicine and biology, it can be used to detect the cancer cell or to do the drug discovery. And for security and defense, you could use this to detect face or do the surveillance. And also in finance, you can also use neural networks to detect fraud or trading. And of course, in robotics, you can use neural networks to do manipulation, like this robot's arms, or to do the motion planning. Perhaps the most famous one is this AlphaGo deep reinforcement learning agent that have already beaten the world champion. But one question we want to ask is that despite of the success of deep neural networks, are they already safe and trustworthy? Unfortunately, the answer is no. So as an example, they are vulnerable to adversarial attacks. So before I dive into the adversarial attacks, I wanted to give you a brief background on neural networks, just in case that you don't have some backgrounds on this. So for example, a 4-layer feed-forward neural network, f of x, with 3 classes is often be plotted something like this. So a neural network is essentially a function that with a very somehow complicated operation. So for example, this represents the hidden neurons, and that will be represented by this nonlinear activation here. So there are many different types of activation, and one of the most popular one is the ReLU activation. So the way you are using a neural network as, for example, an image classifier is that you will take the input x, which is a vector, and send it to this function, and then pass the linear layers, nonlinear layers along to the output to get an output vector. So in this case, because we have 3 classes, so your output vector is of dimension 3. And each component corresponds to the probability or the score for each class. So in this case, suppose our output score looks like this. Then this input, which is an image, you can, if you are in the image classification task, then your input is an image. So this image will be predicted as class 1, because class 1 has the largest score. Okay, and a very brief background on how the machine learning works. So usually you will have 2 phases. First is the training phase, where you are given the training set. That's the training data you have. In this case, if you are training an image classification task, then you will have your training set that could be a bunch of different images for different classes. In this case, the image would be your input X, and your class would be your output label Y. And then you will throw this training data to the training algorithms, and your training algorithms should return a neural network with parameter, which we denote as the symbol W. So once you finish this training phase, at testing phase, you will use your trained model, which is a deep neural network here, and then input a test image to this deep neural networks, and then compute what is the score of this image. So in this case, if the panda class has the largest score, then this image will be recognized as a panda. So let's get back to the adversarial task. So what does the adversarial task mean? So the adversarial task we're talking about happens at the testing phase, where you already finished the training of your neural network, so the parameters are all frozen. So an attacker can appear at the testing phase, trying to craft a very small adversarial perturbation and then add it to your test image, so that now your neural network will think this image is not it's not a panda anymore. For example, here, this neural network thinks this still like the panda-like image to human as a gibbon. So this is called adversarial image because for our human eyes, we can still recognize this is a panda image, but now your neural network cannot recognize anymore. And the reason is because on this adversarial image, your gibbon score now is higher than the panda score. Unfortunately, there are more adversarial attacks than just on the image classification task. So just to give you a few examples, imagine if you're using the camera to recognize the traffic sign. In this case, your camera driven by the machine learning model cannot recognize this as a stop sign. And there are also these 3D adversarial examples that have been shown to fool the machine learning models. For example, they think this turtle is not a turtle, but instead a rifle. Similarly, there are many more other machine learning tasks have been shown to be vulnerable to adversarial attacks. For example, image captioning, speech recognition, and more. Perhaps somehow more surprisingly, deep neural networks are also vulnerable to non-adversarial random perturbations. So it means that now there's no attacker in between, but simply adding random noises on your natural image, and your neural network cannot recognize the perturbed image as well. So I think right now it is the good time to talk about the robustness in AI ML systems. Because right now, the deep neural networks are already powerful enough. They can achieve superior performance, very high accuracy, even better than human. However, what we want right now is to have something more than just good performance. For example, one thing we want is that we want the AI system to produce consistent answers, even when there are perturbations or uncertainties. So when we talk about robustness, there are actually many different aspects. So for example, the distributional shift between training set and test set is also one issue of robustness. Adversarial inputs from attackers that I just described as an example. And there's also this non-adversarial perturbations that could happen, including random noises or model parameter shifts. So in today's talk, I will mainly focus on these two type of perturbation, and I will show you how we can develop robustness metric to evaluate the robustness of neural network upon these two different types of perturbation. Okay, so this is just a brief overview of existing literature. So up to the end of 2017, there are just a few attacks, but since 2018 until now, there are many strong attacks have been developed. But the trend is that once you move on, there's always a stronger attack out there waiting for you. So this is the main reason that we are wondering, like, is attack a really good way to measure robustness? So what is an attacker's goal? If I were an attacker, I wanted to find the smallest input perturbation so that your neural network can get wrong prediction, because I don't want human to be able to recognize there are some additional perturbation added to my test image. So my answer to this question is yes and no. So yes, because it's easy to find one adversarial perturbation by running the attack algorithms. But it's really hard to find the smallest perturbation. And you never know if there are stronger attacks exist. So as I just mentioned, your attack will only become stronger as time goes by. So it's pretty worrisome if you don't know how strong attack will be. Like, you wanted to be able to quantify and to prepare what kind of attack are there so that you can better defend for your machine learning systems. So the motivation is that, can we have an attack agnostic metric, and how? Meaning that, can we develop a metric that is independent of your attack algorithms? And this is the focus of this talk. So there are three fundamental questions. First, how do we define the robustness metric? And second, once we define the robustness metric, how can we compute this metric efficiently? And then finally, can we provide some guarantees on our metric? Okay, so we'll start talking about how do we define the robustness metric. So far, are there any questions? Okay, if not, then we will dive into this section. So this is a cartoon graph for the decision boundary for an ostrich and the given model. So for the triangle part, these are the prediction, the decision boundary for the ostrich, and for other parts, that is for other class. Suppose there's an attacker that can craft an adversarial image for the ostrich here, right? So this is called x0 plus delta, this point. So if we try to measure the amount of perturbation by measuring the magnitude of delta, the perturbation, then for example, this point, the perturbation is on this axis. And then there might be another stronger attacker who can craft an even smaller adversarial perturbation that is closer to the decision boundary. So in general, you want to find the perturbation that is very close to the decision boundary, and the distance we would call is the minimum adversarial perturbation. So we are looking at this problem in a different perspective. So instead of finding an adversarial example, we wanted to quantify a certified robustness region in green here, so that within this region, your predictions are consistent. So we usually measure the region that we will talk shortly. So basically, we can use, for example, the radius to measure how large this region is. And this radius is called the lower bound. The reason that it is called lower bound, because we use the reference as we use the minimum adversarial perturbation as the reference, so that this region, because it is always smaller, so the radius is a lower bound of this minimum adversarial perturbation, while your attack perturbations are upper bounds. So how can we measure the robustness? Basically, characterize this region. So there are three most commonly used distance. For example, the LP norm. So when P equals to 2, that is the Euclidean distance that we often use. And there are also another two that people use in this research field. For example, when P equals to infinity, then the distance is characterizing what is the maximum pixel change that is allowed. And for P equals to 1, that would be the Manhattan distance. So our goal to develop an attack agnostic measure is that we wanted to find what is the largest radius R, so that within this green region, the output of the neural network f of x0 plus delta produce the same prediction for any possible perturbation in this region. So ideally, we want this region as large as possible. So that means it is more robust. I have more guarantees. Okay, so next we will talk about how can we calculate the radius R efficiently. Are there any questions so far? Is this clear, the robustness metric?
Yeah, so I'm following, but if I could ask a question. So in theory, when you're measuring this perturbation R, there is a problem that theoretically you could perturb it such that it actually should no longer be the ostrich class, right?
Exactly. That would be, and you want to find what is the smallest magnitude for that perturbation.
I guess what I'm asking, I don't know if this really ends up being a problem in theory, but so if we say, I don't know, you know, if you have two classes that are actually fairly similar, then maybe a small perturbation doesn't just cause the model to predict a different class, but in fact, humans would agree it should predict a different class. So it's not actually a misprediction anymore. Does that make sense?
Oh, I see. Yes, I got what you're saying. So that is something you can actually do at the output, right? You can, so for example, one way to handle that issue is that you can try to categorize what are the classes that you think it doesn't matter if it predicts as a different class. So you could have a few subsets of like this subcategories that you think in high level, they are all like equivalent class. And in that case, when you kind of reorganize your output class, then you can still do this analysis that the distance or the guarantee we give you here would be like, okay, so this green region would be like all this similar class, although there might be some perturbation that goes to different class, but they will still be the equivalent class.
Okay. All right. Thank you.
No problem. Okay, so now we will talk about how can we calculate this metric more efficiently. So what is the challenge? So unfortunately, it has been shown that if you wanted to find what is the largest radius safety region, that's actually an NP complete problem. So just to give you an example, in this very first formal verification work, that they can calculate this exact radius R, but it takes 3 hours for them to get this number R for just one example, one image, not even an image, just one example that has only a dimension 5 as input, dimension 5 as output, and total 300 neurons. So it is a super tiny networks. So this is very computationally expensive, right? Because you spend 3 hours, but it only can work on this super tiny neural networks. So fortunately, it's possible to find a non-trivial lower bound of this exact maximum robustness radius, meaning that now you wanted to trade off the quality of your robustness region with the computation efficiency. So for example, we can show that if you are willing to give up the tightness of this bound, then you can actually have a polynomial time algorithm to find this radius. So there are a lot of works along this line, and some of the works are from ours. So that's something we will talk about today. So what do we care about the quantification tools? So meaning that the tools that can return you what is the radius R. So the first one is the scalability. So as this motivating example, it's too expensive to calculate the robustness radius for such a tiny network. So we want our tools to be able to scale on a standard data set. For example, some commonly used in computer vision is this MNIST CIFAR data set. And also the most standard one is the ImageNet, which is a pretty large input dimension. And we also want your tools to scale on your model, the size of your model. So for example, some pretty standard deep neural network classifiers, LXNet, BGG16, this has millions of neurons. That's way more than just 300 neurons. So in addition to the scalability, we also care about the provable guarantees. So what does that mean? It means that I want to be able, for example, if I provide you the worst case guarantee, that means I say, okay, 100% within this blue or within this green region, there's no adversarial example possible. Sometimes users might want the probabilistic guarantees, meaning that they are willing to sacrifice a little bit of guarantees into the confidence level. For example, I just want a 95% or 99% of no adversarial example. In that case, you can actually make your region larger. So this is a graphical view of what are the challenges and what are the works that are addressing the challenges. So in one axis, we look at the scale for data sets. Another axis, we look at how complex your architecture is. So this is where the reduplex stands. It can work only on very small input and on a ReLU network. So the first work I will be talking about is an estimation work where you can handle all types of very large scale data sets, very large deep neural networks, but it is an estimation. And then I will talk about the work that can provide you guarantees. And the trade-off is that now you can only work on the smaller data set like CIFAR. It can be extended to complex architecture. So these are the talks that these are the works that I will be talking about today. So I'll be talking about 4 works that the clever score, Fast-Lin algorithm, Cron algorithm, and the proven algorithms, which gives you the probabilistic guarantees. Okay, are there any questions so far? Okay, so the first approach that we can compute this metric, the radius R, is through the local Lipschitz constant. And that is this iClear 2018 work. So we'll be talking about this clever score shortly. So let's revisit the problem. So what is our problem? We have an original input x0, a neural network function f, right? So we have an original image, get the original output, and this is the predicted class. So now our problem is that we want to know what happens to our neural network when your input x0 is perturbed by some jota. So now your input is not just x0, but it's a perturbed image. And your jota have many possible directions with its magnitude be constrained by this epsilon. So with this setting, we want to know what is our perturbed input now? Perturbed output now. So the key idea is that you can use Lipschitz constant to describe the change of the output, basically to describe f at the new input x0 plus jota. So let's look at this 1D dimension example to have the intuition. So the Lipschitz constant here means that for any function here, if you wanted to know what is your output here at some perturbation delta, then your output will always be bounded by your original output minus your local Lipschitz constant times the perturbation magnitude. Similarly, it will be upper bounded also by the local Lipschitz constant. So this is always true. Given a local Lipschitz constant, your output will be bounded, always be bounded by these two terms. So we call this lower bound and upper bound at this point. So if we have this inequality, then we can get our certified radius or the safety region, safety radius, by requiring that your lower bound is greater than 0. So why we can do this? So if you require your lower bound to be greater than 0, then it means that if you define the margin here to be your original class score minus other class score, so if you ensure the lower bound greater than 0, you will ensure the output margin at x0 plus delta to be always greater than 0, then that equivalent means that your original output will always be the highest score. So if you use this, then you can show that your safety region can actually be written out in this form. And then, so what is still missing here? So we show that you can derive theoretically your radius here, and you know that what is your output margin because you know x0. So f of x0 you know, but the only thing you don't know is the Lipschitz constant. So if we can get a Lipschitz constant, then we can find what is the radius here. So in the work, we try to find a Lipschitz constant by using the definition of this. So if you look at this, the definition of Lipschitz constant is the maximum gradient norm that's kind of bounding the change of your output function. But because your F is a deep neural network, so this is a very nasty objective, which is hard to solve to the optimal. So you can do the sampling in the work that we describe with the extreme value theory to estimate what is your Lipschitz constant. So your algorithm would look like this. You will generate a bunch of samples around your image. And then you will do the backpropagation to find out what is the gradient at this green point. So you can directly estimate your gradient norm by taking the max of them as the estimation, or you can use the maximum likelihood estimation to fit to the extreme value distribution. Finally, when you have this Lipschitz constant estimation, then you can give the clever score, which is the radius that you estimate. So as an example, here are the experiment results. So we show the clever score and the CW attack, which is a very strong attack for L2 norm. We went through different data sets, these 3 benchmark, and then compute what is the clever score, R, and the CW attack, the perturbation, adversarial perturbation you find at its smallest. So what can you see? You see that our clever score is very close to the CW attack. But you might notice here, your clever score is greater than the CW attack on some cases. So this could be potentially problematic because ideally we want to have a certified lower bound that will always follow this order. So your lower bound should be always less than the magnitude of attack, while here you have the opposite. So the next question we ask is that, can we actually have a certified robustness lower bound? And that is also attack agnostic. And fortunately, the answer is yes. And that will be the two methods that we will introduce here. So this is called the linear bounding framework that was published in this two conference in 2018. So now we will talk about this Fast-Lin algorithm and the Crown algorithm so that you can get this robustness certificate that's always the certified lower bound. Okay, are there any questions so far?
I have a quick question. Is it possible to kind of adapt these robustness metrics to something like natural language processing, where you might not have like continuous perturbations, but might have like bigger perturbations, like maybe if you substitute synonyms or misspellings, that sort of thing?
Right, so for example, like an L0 norm could be like some surrogate. So the L0 norm is not measuring the exact distance, but what are the non-zero elements in the norm. So that could be something that you can apply to the discrete setting.
Okay, thanks.
No worries.
I
Okay.
wonder, I have a question. Does your R depends on the architecture, on a, network architecture?
Yes, so remember
Okay.
this R depends on two things. One is your image X0. So different test image could have different R, which is very natural because you can imagine some of your image is closer to the decision boundary. They might have smaller certified radius. Some image, they are far away. They might have larger certified radius. And it also depends on your model. So because the attack happens at the inference stage, so your model parameters are frozen. So basically the robustness radius could be different for a different model, even for the same image.
Okay, thank you. And I've seen Q in one of your formulas. So what is the relation between P and Q? Like sum of the reciprocals equals 1, something like this?
Where's the Q?
There was Q.
Oh, yeah, so the Q there means the dual norm. Let's see. Oh, yeah. So the Lipschitz constant is actually a dual norm of your P norm perturbation. So if you are perturbing your input in the P norm, then your Lipschitz constant will be the Q norm in Q norm. So they are dual norm, yeah.
Mm-hmm.
Okay, great. So recall earlier that we try to use local Lipschitz to describe the range of your output perturbate, like your output at the perturbed image. Right, we use the Lipschitz constant to characterize the perturbed image. However, we didn't really explicitly exploit your architecture, your activation status, so on, right? So that is something we will exploit right now. So the question is, how can we exploit the activation status, for example? So here's the key idea. If we can calculate the lower bound and the upper bound analytically, then we can just do the binary search to check this condition if your lower bound is always greater than your upper bound of other classes. And we talk about that. The reason that we check about this is that we want to make sure your output of your original class at the perturbed image, that will always be the greatest, highest score, so that if you can have this condition hold, then you will ensure that your output of the original class will always be the highest score, so that the prediction will not change. So what do we have now? We have the perturbed image with some perturbation constrained by the p-norm. The first step we do is that we specify what is the epsilon. What is the magnitude you want to know for the safety region? And then we propagate a bound layer by layer. Finally, we get the bound at the output, and then we can check if the lower bound of the original class is greater than the upper bound of other class. So now the key is that how do you get this lower bound and upper bound analytically? So here comes the second key idea. We can actually apply this linear bound on the ReLU activation, which I will describe shortly how we can exactly do that. But if you apply linear bounds on these nonlinear activation, then you can show that your neural network output, which is a nonlinear, non-convex neural network, can be bounded by two linear bounds, a linear lower bound and a linear upper bound for all possible perturbation. So once we have this linear inequality, then we can get what is the analytic bound through the optimization, right? So we can maximize this upper bound, that is a linear function of f of x, with respect to your norm constraint on the perturbation. And so solving this maximization problem gives us a constant upper bound for all possible perturbation. Similarly, we can get a global lower bound by minimizing the linear lower bound. So the algorithm roughly looks like this. So we can categorize your neurons into three different status based on what is the input of the neuron, right? So if your input, for example, we will discuss the detail very quickly later, but basically you would have three possible status of your ReLU neurons. And then we can kind of unwrap this nonlinear activation from the case layer to the k-1 layer, so that your output map will always be bounded by the previous layers. So you see that originally zk plus 1 is related to zk. Now with some manipulation, I can connect to the zk-1. So I move backwards from the output to the input. And when you do this iteratively, then you can connect your certain hidden layer to the input as a linear function. So let's look into more details, how exactly the steps work. So the first possible status of your neuron is that if your input range L is positive, then your ReLU is essentially just a linear function. If your upper bound is less than 0, then your ReLU will be dead. So the most tricky case is that if you have your L, lower bound, to be negative, upper bound to be positive, then you are not sure if your ReLU will activate or not. So in this case, in every case, we can actually bound your ReLU by two linear bounds. So for example, In this case, because ReLU is just linear function, so you can choose the slope and intercept to be just a linear function, so there's no bounding here. Similarly, if your neuron is dead, then you will just use y equals to 0 as this line. The interesting part is that if you have an uncertain neuron, then you can use two linear bounds to bound this. So you can calculate what is the score of this line, right? Because you know that it will pass this L0 point and also this UU point, so that you can calculate what is the slope and intercept for this upper bound and the lower bound. Next, once you have this linear bound for your nonlinear ReLU activation, then we can unwrap the K+1 layer to the case layer. So the key is that you can decompose your weights to the positive part and the negative part. And then once you do this, you can show that now you can have an upper bound where that will relate your K+1 layer to the K layer. So you see that by applying the upper bound, we can remove this nonlinear activation, right? So there's no sigma here, but instead replaced by the linear bound parameters alpha and beta. Similarly, you can have these negative weights related to your lower bound. So if you try to put these two terms together, then essentially this will be in a form like this. So your zk+1 will be less than a times zk plus some constant, right? So far you have successfully removed the nonlinear layer sigma. So what can we do? The next step is to plug in what is zk, right? So this is basically the definition of the case layer. Sorry, there's a bug. There's a bug here. All right, so there's a case layer. You plug in the definition here so that now you see that these A are different A's, but for the notation convenience, I use the same A. But these are different linear coefficient, and now you relate K+1 layer to the K-1 layer. So did you notice what is the difference? So these two terms are very similar, right? Basically, they are having a linear layer, linear matrix multiplication here times a nonlinear feature vector. But now you successfully move from zk to zk-1. So because they are in the same form, you can imagine we can do this operation again and again, so that eventually you get what is the relation between zk+1 to input x. Okay, so now we get what is the form of your f, right? So your f, sorry, this is a typo, it should be FL, but these are the linear bounds you have. So if you look at this optimization problem, it's actually a very nice optimization problem, right? Because I have a linear objective and convex constraint. And luckily, we can actually solve this by Holder's inequality. So we get the analytic form for the upper bound and lower bound. So this will be your full algorithms. First, you will specify epsilon. Now you propagate a bound for each layer using a formula we just derived. You get the output bound and check if the original lower bound is greater than the target class, other class upper bound? If yes, you can increase epsilon, otherwise decrease epsilon. So we can find out what is the largest epsilon you can get for the certified radius. Sorry, there's this cockroach. Okay, let's continue. All right, so there's we do some experiments here on the MNIST network. So we compare to this 4 different methods here. So basically, we compare on the toy example, that is the place where we can use reluplex to get the exact answer. So this is the perturbation that we have normalized. So basically, what does this mean? It means that if you perturb your image within, the perturbation is within 6%, then we guarantee that there will be no misclassification. Well, in the tag algorithm, they find out if you perturb the image by magnitude by 16%, you can find one adversarial perturbation. And the maximum certified radius we get is 15% by reluplex. Okay, so our algorithm is similar to a linear programming approach, also close to the reluplex by roughly 2 to 3 times, but much faster. So it's 2 to 6 orders of magnitude faster than other algorithms. And let's look at a larger data sets and model. So in these networks, the reluplex are not feasible. Well, we can still use Fast-Lin algorithm to find solution, and linear programming approach is not feasible after 4 layers. So again, we show that our results are very similar to a more complicated verification methods, but it's much faster. So the next question is, what about other activation functions? So for example, if you have a 10-edge activation, how can you do? So now we can still use the same idea, right? So still, based on the signs of the lower bounds L and U, you can divide them into 3 cases. First one, activated, you can still have 2 upper bounds and lower bounds, always inactivated, roughly inactivated case, and uncertain case. Similarly for sigmoid and for ReLU. So there's a heuristics for ReLU. For these 2 cases, if your neurons are in this status, you basically have no changes because you are using an exact bound. The interesting case is that when you have an uncertain neurons, you can do something smarter, right? So for example, if your U is much larger than the absolute value of L, you want to use y equals to x lower bound because you overlap more with the y equals to x part. On the other hand, if you have your L much negative than U, then you have more parts that is dead. So you want to use a lower bound that is y equals to 0. Okay, so this is called the Crown algorithm. And it's very similar to the Fast-Lin algorithm. The only change is that instead of using 1 linear coefficient, now you are using 2 linear coefficients. Then that is the only changes. So if we look at the comparison using the ReLU heuristics, then you can roughly have 25% of improvement on the tightness of the bound, but you also get roughly 100% overhead. And the reason is because now you need to calculate 2 linear coefficients instead of 1. So far we talked about these algorithms: Clever Score, Fast-Lin, and Crown. So we don't talk about today, but if you're interested, I would encourage you to check in this CNN-Cert that can handle this more complex neural network architecture, and we can also get a certificate for using the Lipschitz constant approach. So the challenge here is that how can we get a certification for very deep, very large neural networks? And next, we'll talk about how can you get the robustness certificate for a non-adversarial input perturbation. Are there any questions so far?
Professor Weng, I don't know if you're going to talk about this at the end of your talk, but I'm curious, as the networks get larger, as they get deeper, I would imagine that these robustness regions get smaller because all the layers sort of just multiply the possible errors. And so beyond the theory, are these regions large enough to be, I don't know what the right word is, useful? Because if you say, you know, oh, well, I've proved that you have no misclassifications if you modify it by less than 0.000000001%. Well, that's not telling me much information, right?
Yeah, that's a good point. That's a very great question. Indeed, yes. So the limitation of this interval bound is basically if you have deeper neural networks, because you do more bounding so that your perturbation, the certificate you can get will be smaller. But fortunately, we can do robust training by including this verification bounds. So if indeed for the standard network, your bounds may be very, very small if it's not trained with this verification bounds. But if you train with the verification bounds, you can make this perturbation much, much larger to be useful.
Okay, awesome. Thank you.
Yeah, no problem. Okay, so next we'll talk about how do you handle a non-adversarial input perturbation. And now it is for the probabilistic guarantees that we publish in this ICML paper. Okay, so the challenges in the probabilistic quantification is that the earlier work, they mostly have to have some assumptions that's usually hard to verify. For example, what is the shape of your decision boundary, something like that. So the goal here is that we wanted to be able to provide a probability certificate without using any of the assumptions that we cannot verify. So for example, instead of telling you 100% guarantee of no misclassification, now I relax the guarantee to 99%, for example, but now I wanted to know what is the corresponding safety region, safety radius. So the key idea is that we can build upon our existing linear bounding framework that we just talked about. And the idea is that the CDF of your function output will also be bounded by the CDF of your linear lower and upper bound. So we basically can bound the probability by the two probability that takes account into your linear bound. So why is this good? Because linear function, that is easy to calculate, right? Because imagine now you have a random variable, a random vector, a linear combination of a random vector random variables can be bounded by some probabilistic inequalities like Hofstadter inequalities. So now you can actually find out what is this probability analytically. Similarly, for Gaussian noises, you can actually find what is the CDF and to get its probability exactly. So this is called a proven algorithm. Everything are very similar, except that now you need to specify what is your random noise distribution and what is the confidence you are willing to have. And you propagate a bound through the worst case bounds that we talk about. And now at the output, you find out what is the probability by this analytic form. So you will check that if this probability is greater than your confidence. If yes, you can increase epsilon, otherwise decrease it. So this table shows that with only random perturbation, it's possible to attack your neural network with non-zero attack success rate. And this is what we have for the proven bound results. So compared to the worst case bound, if you are willing to give up 0.01% of confidence, then you can make your certified radius much larger. Similarly, for other networks on MNIST. And this is the result for the CIFAR and adversarial trained model. So this is the summary of this talk. So today I talk about the robustness metric for the deep neural network classifiers. I talk about we can define the certified radius R. And we talk about 4 algorithms that we can find this R, including clever score, Fast-Lin, Crown, and proven. And the tools that we develop are efficient. It's roughly 2 to 6 orders of magnitude faster than modern works. So below are some relevant and follow-up works, including, I already told you that you can extend this framework to CNNs. You can also extend this to the RNNs, LSTM, and GRU, and that would be the methods called popcorn. You can do robust training. So that's what Ted was just asking, that how we can improve the certified radius by using the training. And we will also have a work on the semantic certificate. So the idea here is that instead of having the change on a pixel, in computer vision, people care more about the semantic perturbation. For example, rotations, color changes, shift, contrast, and so on. So our work we talk about today can actually be extended to handle this semantic perturbations. Okay, so I see I have 10 minutes that I can talk about what's next. But before that, I wanted to ask, are there any questions so far? All right, if not, then let's talk about what are some new challenges or remaining challenges. So the first part is that we don't have time to talk about today, but basically you can design your training algorithms to incorporate this verification bound, and that's called robust training or verification-based training, so that you can enhance the certified radius for your neural network models. There's also this recent scalable verification techniques where the key idea is that instead of looking at this single point, right, because this is very close to the decision boundary, so you can imagine the robustness certificate will be very small. But if you change your classification rule to this smoothing, so instead of deciding the output prediction by this point, you will decide by an ensemble of this point. So in this case, you are smoothing your decision boundary so that this can resist larger perturbation. There's also other possible attacks that could happen. So today, we only talk about adversarial attacks and non-adversarial attacks in the inference time. But you could have this data poisoning happening in the training stage, and this will be more complicated than the setting that we consider. Also, you might have some error injection attack that could change your model parameters. So what would be the corresponding certificate and defense as something an active research area? Finally, today we only talk about supervised learning task, classification. If you have a deep RL agent, we show that it's also possible to attack your RL agent so that you see now with the adversarial perturbation, it cannot work properly. So in my lab, we care about these three things. We care about the scalability, efficiency, and approval guarantees. So this is the end of today's talk, and thank you. And let me know if you have any questions.
Thank you so much, Professor Weng. Does anybody have a question they would like to ask?
I have two questions. First, would you please mention what is adversarial training? And the second question is, what are the notions for doing adversarial attack as well as adversarial defense in terms of video data? Thank you.
In terms of what video data?
Yeah, video data.
Okay, so for the first question, the adversarial training. So you might see robust training, adversarial training. So adversarial training is more referring to solving a min-max problem. So solving a min-max problem, you can solve this alternatively and by inserting the attack algorithms into your training procedure. And that's we often call it adversarial training. So robust training generally consists of adversarial training and verification-based training. So in the verification-based training, we basically, instead of inserting the attack algorithms, we are inserting these verification algorithms into the training. So does that answer the first part, the first question you have?
Yeah, thank you.
Okay, so for the video data, it depends how you are going to, what is your model, right? If you are going to use some recurrent neural network, then it will be very similar. You can try the popcorn, that is a follow-up work of this, what we have done for the classification, but that's one possible way to handle the video data.
In robust training, that includes adversarial training plus verification training. Am I right?
Verification-based training, yes.
Okay, verification-based training. And for video data, you mentioned about adversarial training for both computer vision as well as RNN.
Right, so all these things you can do for no matter which model. So the thing I talk about today, you can do this for the classification task and also regression task. So by adversarial training or verification or adversarial attacks, these all works.
Thank you. Thanks a lot.
Okay.
Any other questions? So if I could ask a question, I'm not sure. I hope my internet connection's still good. I was curious, Professor Weng, are there any techniques that people have looked at to try to, protect against adversarial attacks? So like say, add some Gaussian noise, do some smoothing or whatever on the input before, sending it to your classifier or things like that. And whether or not you've considered quantifying how those approaches, how much they increase this radius, or not, as the case may be.
Yeah, that's a great question. So that's actually the scalable verification. So the key word would be randomized smoothing. That's pretty popular in recent, like last 2 years. So the good thing for this randomized smoothing is that instead of training, like say, if I do adversarial training, I need to touch my model parameters. But if you do randomized smoothing, you are doing something like post-processing. You don't need to retrain your model, but actually you are trying to like insert a module at the input so that you change your prediction rule. So now you look at, instead of output is the prediction of X0, now you look at what is the probability of each class if your input are X0 plus some Gaussian noise. And there in the paper, they show that you can derive actually the certified radius analytically as well, so that you can actually calculate the certified radius very easily.
Okay, that's really cool. Thank you.
Yeah, no problem.
Okay, I think we have time for one more question if there's anybody else. I'm not sure if there's one more. All right.
If you're interested, you can visit my website or send me emails. So we have a few follow-up works that I would encourage you, if you're interested, feel free to look it up, and I'm happy to discuss and chat.
Okay, awesome. Well, we really appreciate you joining us. This is very cool research. I'd love to see how you've brought your mathematical thinking to this problem of the robustness of our neural networks. We love them, but it's good that somebody's looking at how to quantify how safe our predictions are. So thanks again for joining us tonight. I think unfortunately we had you talk long enough. Maybe we need to give you a chance to rest your voice.
Yeah. I just had a class today, so not a very good condition.
Yeah, pile that on top. But so thank you so much for joining us and adding to the length of your day with us today.
Yeah, thanks for having me. Thank you.
All right. Well, thanks everyone. Thanks for joining, and appreciate all the engagement, all the questions. We will be continuing our book club at noon on Saturday. And then stay tuned. After the holidays, we'll be working again with HDSI to schedule more events in the new year.
Okay, thanks everyone. Thank you, Ted.
All right, thanks. Good night.
Thanks.
Bye.